How does a bumper car move on an uneven floor? The answer to that question is that the bumper car accelerates in the direction that reduces its total potential energy as quickly as possible. I hope you're thinking, wait a second, a bumper car accelerates in the direction of the net force acting on it. That's part of Newton's second law. Why is Lou talking about potential energy? Your observation about bumper cars' acceleration is exactly right. It does accelerate in the direction of the net force acting on it. But my observation is also right. It does accelerate in the direction that reduces its total potential energy as quickly as possible. This is another big picture moment. Forces and potential energies are intimately related. After all, potential energy is energy stored in forces. When I lift this ball upward, I'm doing work against the gravitational force it experiences. It's downward weight, and it stores my work as gravitational potential energy. So I'm doing work against the same force that stores that work as potential energy. When I let go of the ball and it becomes a falling ball, it accelerates downward because that's the direction of the only force acting on the ball. It's downward weight. And because that's the direction that reduces its only potential energy, its gravitational potential energy, as quickly as possible. Two reasons simultaneously, but they aren't two separate reasons. They're the same reason looked at from different perspectives. The ball accelerates downward because that's the direction of the net force on it, and the ball accelerates downward because that's the direction that reduces its total potential energy as quickly as possible. Same reason, two perspectives. The direction of the gravitational force on the ball is the direction that reduces the ball's gravitational potential energy as quickly as possible. Another example, a rubber band. If I hold one end still and I stretch to the other end, in this case, the left end, outward, I do work on it against the elastic forces of the rubber band, and the rubber band stores my work as elastic potential energy. When I release this left end of the rubber band, it accelerates inward because that's the direction of the elastic force on it, and because that's the direction that reduces the rubber band's elastic potential energy as quickly as possible. Once again, those aren't separate reasons for the end's acceleration. They're the same reason from different perspectives. The direction of the elastic force on the left end of the rubber band is the direction that reduces the rubber band's elastic potential energy as quickly as possible. But lest you think that this discussion is pointless and repetitive, let me show you one more example. When I lift one end of the rubber band upward, like this, I'm doing work against both an elastic force and a gravitational force at the same time. And it's storing that work as two separate potential energies at the same time. And when I let go of the other end, the bottom end of the rubber band, it accelerates, but figuring out why it chose that direction and stuff isn't so easy. How would you figure out the net force on that rubber band? Actually, the rubber band isn't even a single object. It's this big floppy thing, and each piece of the rubber band had its own individual acceleration based on its own individual net force. Things are pretty complicated. Well, rather than trying to identify the net force on each individual part of the rubber band, sometimes it's easier just to think in terms of total potential energy. Since individual forces are associated with individual potential energies, net force is associated with total potential energy. That is, sum of all the potential energies that an object has, that's the total. And an object accelerates in the direction that reduces its total potential energy as quickly as possible. That is a universal rule. So you can think of it kind of as a fancier version of falling. An ordinary falling ball accelerates downward so as to reduce the only potential energy it has, gravitational potential energy, as quickly as possible. A ball that has many different potential energies, like this one, will accelerate in the direction that reduces all of its potential energies, the sum of them, as quickly as possible. So it's kind of a fancy version of falling. I don't even know which way this thing's going to go. Let's try it. Like that. Okay, well, this episode is about bumper cars, so it's time to bring bumper cars into the picture. Like anything else, a bumper car will accelerate in the direction that reduces its total potential energy as quickly as possible. And that turns out to be a useful way to predict a bumper car's motion when the arena isn't flat and level. So let me get out my miniature bumper car arena and let's take a look. So here's my miniature bumper car arena again. And right now the bumper cars don't accelerate at all, at least when they're by themselves, because the arena is flat and level and there's no direction they can travel to reduce their total potential energy, quickly or not quickly. But if I tilt the arena, something you don't normally do at the amusement park, now there is something they can do to reduce their total potential energy. The only potential energy they really have to work with right now is gravitational potential energy. And if they go up to this high side of the bumper car arena, they have more of it than if they're at the bottom. So if I let this guy accelerate, which way do you think it's going to accelerate? It tries to reduce its total potential energy, and it accelerates in the direction that reduces its total potential energy as quickly as possible. Now, this is really a glorified ramp, and we know what things do on ramps. They accelerate downhill on ramps. But if we forget that and just deal with the general rule, we notice that, wow, there are ways in which objects on this surface, bumper cars on this surface, can increase or decrease their total potential energy. And I wonder which way this bumper car will accelerate. It will accelerate in the direction that reduces its total potential energy as quickly as possible. And look at the paths it takes. These lovely arcs. These are sort of a fancy version of falling objects. It's moving sideways, falling on a ramp. And the coherent overarching idea is this acceleration so as to reduce total potential energy. Well, if you played bumper car on this surface, it would be exciting. You would spend a lot of time probably at that end of the arena. And if the arena weren't just simply tilted, as I've done here, but rather had complicated undulating surfaces, you, as you drove along in your bumper car, would find that it was always accelerating in the direction that reduced its total potential energy as quickly as possible. It would tend to accelerate down into the dips, the low points on the arena surface, because that's the direction it can go to reduce its gravitational potential energy. When bumper cars collide and are pressing against each other, there's also elastic potential energy involved, and the acceleration acts to reduce that potential energy as well. So, life on a bumper car arena, with all of its complications and various ways in which to store energy, various potential energies, has accelerations always in the direction that reduces the total potential energy as quickly as possible. It's time for a question. This giant pendulum has a bowling ball at the bottom and it can swing back and forth, like as you see. Notice as I pull it away from center what happens to the height of the bowling ball, because this is going to be important in the question I'm about to ask you. As I pull it away from center, look what it's doing. So the question is this: when I let go of the bowling ball, in which direction will it accelerate? When I let go of the bowling ball, it'll accelerate forward, because that will reduce its total potential energy as quickly as possible. Off it goes. Actually, this is a fun version of the experiment. If I hold the bowling ball like this and let go of it, it will accelerate forward until it reaches the low point. Then it'll keep going and accelerate backwards as it goes away from the low point. It'll reverse its direction, continuing to accelerate back toward the low point, overshoot, and come back and visit me. But it won't go any farther than you see it right now, because doing so would require it to create energy out of nothing. So let's watch it go. Here it goes. See, it worked. I'm getting tired of saying it accelerates in the direction that reduces its total potential energy as quickly as possible, and you're probably getting tired of hearing me say it. So I'll introduce one more really useful concept: gradients. A gradient is a gradual variation in a physical quantity near a particular position. You've seen gradients before and perhaps even called them gradients. This is a brightness gradient. Brightness is a physical quantity, and the brightness of this rectangle here increases gradually from here to here. Don't you love video? One of my favorite examples of a gradient is a scent or fragrance gradient. If you watch a dog searching for food with its nose, you'll see that it's constantly measuring a scent gradient. Once it detects the scent of food, it sniffs around, trying to figure out the direction in which that scent increases most rapidly. It moves up that scent gradient and eventually reaches the source of the scent, which is the food, and it eats the food. So a gradient is actually a vector quantity that points in the direction that its physical quantity increases most rapidly. So if the scent of the food is increasing from here to there, that's the fastest path for the scent to get stronger. That's the direction the dog moves, and that's the direction of the scent gradient. The dog moves in that direction, that is up the scent gradient, because that's likely to be the shortest path to the food. The dog goes up the scent gradient and finds the food and eats it. So nature is actually full of creatures and plants that travel up or down various gradients. They go up or down chemical gradients, they go up or down temperature gradients, light gradients, and so on. So this concept of a gradient is very useful in physics, and we'll encounter gradients in many different contexts in future episodes. The gradient that is relevant to this episode is the potential energy gradient. For example, this ball's total potential energy varies with its position. The only form of potential energy that it really has to work with is its gravitational potential energy. So its total potential energy increases as I lift it higher and higher. So this is the direction in which its total potential energy is increasing most rapidly. That is the direction of its total potential energy gradient. So you can sort of think of the ball as kind of sniffing around. Where is its total potential energy increasing the most? Oh, it's going upward. This is the fastest increase in total potential energy. That is the direction of the ball's potential energy gradient, total potential energy gradient. And if I let go of the ball, it accelerates downward, opposite the total potential energy gradient. That's a general observation. Any object accelerates in the direction opposite its total potential energy gradient, because that is the direction in which its total potential energy is decreasing as rapidly as possible, and that's also the direction of the net force on it. It all comes together. Objects accelerate opposite their total potential energy gradients, because that's how that's the direction of the net force on them. So, back to bumper cars. In my crazy little tilted bumper car arena, a bumper car has a potential energy gradient. As it goes up the slope, its total potential energy is increasing. So that's the potential energy gradient for it. And if I let go of it, it accelerates opposite that potential energy gradient, namely down the slope. In general, in a real bumper car arena, those of you who have tried this, the floor is typically not perfectly smooth. It's got some undulations in it, wear and tear, and how it was made. And at any location, the bumper car will accelerate down the local potential energy gradient. In effect, it sort of examines the local potential energy, and it finds the path in which that potential energy is decreasing as rapidly as possible. That's down the local total potential energy gradient.